Now let's look at this equation, this example number 11.7. So this is called the seesaw problem. So you have a father of mass mf and his daughter of mass md sit on opposite ends of a seesaw at equal distances from the pivot point. So this is mf here. So this is the force of gravity. Um, this is the mass of the daughter. This is the force of gravity right here. And we know that the length of the seesaw is L, and this is the center right here. So we want to find an expression for the magnitude of the system's angular momentum. So if you want to calculate the angular momentum, so basically, so we have the angular momentum of the seesaw. So if the seesaw is we can think about this as a thin rod that has a length L and is rotating about the center. So it means that the moment of inertia about the center of mass is 1/12 ml squared. So the total moment of inertia I is the moment of inertia of the thin rod plus the moment of inertia of the father. So it's just the mass of the father times L/2 squared plus the moment of inertia of the daughter is mass of daughter times L/2 squared, and all of this is equal to this quantity right here. Then now I can calculate my L as I times omega, which is given by this expression right here. So just multiply the I value by omega. Now for part B, I'm going to find an expression for the magnitude of the angular acceleration of the system when the seesaw makes an angle of theta with respect to the horizontal. So if I want to find the angular acceleration at this particular configuration right here, when the seesaw makes an angle of theta with respect to the horizontal, then the first thing that I need to do is that I need to calculate the torque from the father. So the torque is just the m, so mass times gravity times L/2 cosine of theta. Now the reason why we use cosine of theta right here is because, again, when I calculate the torque, I only need to use the component that makes 90 degrees with respect to my axis. So if this is my axis right here, I know that if this angle right here is theta, then this angle must be equals to theta as well. And if this angle is equals to theta, then notice that if I do a little bit of trigonometry right here, then I can take this force and break it into one component that is at 90 degrees with respect to my displacement vector here, and one component that is parallel to the direction of the seesaw. So if you do this very carefully, there is going to be some angle right here, which is like, this would be theta as well. So with a little bit of trigonometry here, you can show that the torque produced by the father is given by this equation, and this is going to be in the counterclockwise direction. Then I can calculate the torque produced by the daughter. So this will be given by this. This will be pointing in the clockwise direction. So this is negative torque. And so if you sum the two contributions together, you get this quantity here. And since I know that alpha is equals to the sum of all the torque over I, and we've already calculated what the I value is, then I can solve for alpha to get this quantity right there. Okay. So now we're going to do a little bit. We're going to look at a system that is an isolated system. So an isolated system simply means that there is no external torques acting on the system. So if there is no external torque acting on the system, this means that the derivative of the angular momentum vector with respect to time must be equals to 0. So if the derivative of L with respect to time is equals to 0, it means that the change in the L must be equals to 0. Now what this means is that L initial must be equals to L final. So it means that the angular momentum is not changing. Now this is an example here where, so if you look at a skater, so you can look at one picture here where, so his arms and legs are kind of close to his body, and so this means that the skater's moment of inertia is small and his angular speed is large. So basically, for the skater to slow down, what he does is that for him to slow down, he's going to move his his arms. So open up his arms and legs. So when he open up his arms and legs, he increases his moment of inertia, and so that way he can reduce his speed. So basically, this is the equation that we're talking about. So we're looking at the L is equals to I times omega, and then if this is equals to constant for an isolated system, the total L is not changing. So it means that I1 omega, I initial omega initial is equals to I final omega final, and this is equals to a constant. All right. So generally, for an isolated system, the energy of the system does not change. There is no net external forces acting on it. It means that the linear momentum is not going to change. And if there is no external torque acting on the system as well, it means that the angular momentum as well is not going to change. All right. So basically, when we solve a problem, this is like the main equation that we're going to use here. So we're going to say that the angular momentum before, the moment of inertia before times the omega I must be equals to the moment of inertia after times the omega final. So this is called the law of conservation of angular momentum. Now let's look at one final example here. So this is example number 11.7. And in this example here, we're going to look at the merry-go-round. So we have a horizontal platform in the shape of a circular disc, and this is going to rotate freely in a horizontal plane about a frictionless vertical axle. The platform has a mass of m, which is equals to 100 kilograms, and a radius of 2.0 meters. And so we have a student who has a mass of 60 kilograms that is going to walk slowly from the rim of the disc towards its center. So what we're going to do is that we're told that if the angular speed of the system is 2.0 radians per second when the student is at the rim, what is the angular speed when she reaches a point R, which is given by 0.5 meters from the center? So this is the picture of the problem that I'm going to solve. So this is the platform, this is the radius, this is the center, this is the axis. So this is rotating in the counterclockwise direction. So this is the student right here at the edges. So what she's going to do is that she's going to move towards the center. And so we can use this equation here for conservation of angular momentum. So we're saying that before, we just add, so the I value is calculated by adding the I value of the disk plus the moment of inertia of the student, which is just the mass times the distance squared. So when the student is at the edges, the distance is the radius. Now when the student walks towards the center, then the distance becomes this lowercase r right here. So if you put those two equations together, you can solve for the final value of the angular velocity, which if you substitute here, you get this quantity right here. So notice that the angular velocity has increased from 2.0 radians per second to 4.1 radians per second. So the angular speed has increased because the moment of inertia has reduced. Now, if we want to calculate the kinetic energy of the system, we can calculate the kinetic energy before. It's going to be 880 joules. It's just given by this equation right here. And the kinetic energy after is given by this equation, which is going to be 1.80 times 10 to the 23 times 10 to the 3 joules. And so you can see that there is an increase in the kinetic energy. So even though there is a decrease in the moment of inertia, but the increase in the kinetic and the increase in the angular speed is playing a much more important role because the increase is way greater. So this is almost like a 100% increase in the angular speed. So going from 2.0 to 4.1 is almost like a 100% increase in speed. Meanwhile, there is some decrease in the angular momentum, but when you put everything together, there is some decrease in the moment of inertia from 440 to 215. But because when we calculate the kinetic energy, the rotational kinetic energy, it goes as the square. So we take the square of the angular speed. So we end up getting a larger value of the kinetic energy compared to, so after it's 1.8 times 10 to the 3 joules, before is 880 joules. So there is an overall increase in the kinetic energy.